Okay, so welcome everyone to the second session of the first day. The first speaker is Professor Ira Gessel from Brandeis University, and his title is Problems in Enumerative Combinatorics.
Thank you. I'm going to talk about some, problems, but there may be a better description of what I'm talking about is some interesting things that I've come across in my years as an enumerative combinatorialist, things that I think are interesting but I don't really understand. And so some of them aren't really so much specific problems as just here's something that looks interesting to me, but can we say something more specific about it? So a lot of these deal with positive integers with interesting generating functions. So whenever an enumerative combinatorialist sees positive integers, we ask if there's a combinatorial interpretation. That's kind of the most natural problem. But even when there aren't combinatorial interpretations, there are interesting things that we might be able to say about these numbers. So here are some cases I've come across where we have interesting generating functions, at least in my opinion, where in some cases we have combinatorial interpretations, and in most cases we don't. So here is one of my favorite examples. I've talked about this before. Some of you may have heard me mention this, but probably most of you haven't. These are three rational power series in three variables, and they all have non-negative coefficients, and there are no known combinatorial interpretations for any of them. And they're all actually closely related in the following way. So there are no known combinatorial interpretations. If we know that b of x, y, z has non-negative coefficients, that implies that a does also, since a can be expressed in terms of b this way, in this transformation that preserves non-negativity of the coefficients. And similarly, the non-negativity of c implies the non-negativity of b. Notice that a and b are symmetric and c is not. So how can we prove this non-negativity? Well, there's one fairly straightforward way of proving the non-negativity of the coefficients of c, which also implies the non-negativity of a and b. The coefficients of c are basically squares. So more precisely, the coefficient of a particular monomial in C is 0 under some inequalities on the exponents. And if on other inequalities, we have this explicit formula. It's a square times a quotient of factorials, which is clearly positive. So this was shown by Ismail and Tamhankar using McMahon's master theorem. Now, if we wanted to try to get a combinatorial interpretation out of this, we have two problems. One is that sum is the thing that we're squaring is an alternating sum, and it's hard to figure out exactly what the sign is. There doesn't seem to be a simple pattern in the sign. So whenever you have a square, we know that we have a non-negative integer. But if we don't know the sign of the thing, it's very difficult to give it a combinatorial interpretation. So another problem with trying to interpret it is that the square is multiplied by a factor that's not an integer. Well, it's not at all hard to prove that that expression is an integer because we can write it as a product of two alternating sums that are clearly integers, and we get that by using this formula that says if you have a product of two binomial coefficients, you multiply it by that quotient of factorials, you get a product of two different binomial coefficients. So this is a very elementary fact, but it means that this product is no longer the product of something with itself. So we no longer have a square. Okay. There's an interesting, completely different proof of the non-negativity of b of x, y, z. And I don't know of any connection between these two. I don't know of any way of sort of generalizing these two proofs to give you something more general. So the non-negativity of b follows from the stronger statement that the coefficients of this fraction, which is no longer rational, you have a square root of 1 minus 4xy in the numerator, that the coefficients of this thing are non-negative. And since then, b of x, y, z is the product of two non-negative series. And the reason why this quotient has non-negative coefficients is because there's a simple explicit formula for these coefficients. So again, we have some inequalities that split it up into a few cases, but in each case, this coefficient is a quotient, an explicit quotient of factorials. And notice that this formula as a quotient of factorials does not make it obvious that these coefficients are integers, but it's pretty clear from the generating function that they are integers. So this brings up another and that is integer quotients of factorials. So we all know that the binomial coefficients, a plus b factorial over a factorial b factorial, those are integers. But there are a lot of other quotients of factorials that are integers that are not so obvious. Generally, it's not so hard to prove that these quotients of factorials are integers using the sort of standard way is by computing the power of a prime dividing these factorials. But in most of these cases, we don't have any combinatorial interpretations. And these numbers are often somewhat interesting, and I'll say more about them later on. So these coefficients in particular are what I call super Ballot numbers because in the case c equals 0, they reduce to Ballot numbers. So I don't know of any combinatorial interpretation for them. Some special cases, if you look at the case of s of m plus n and m minus 1, these are what I call super Catalan numbers. T of 1n is the nth Catalan number. T of 2n has this fairly simple formula. And there are nice combinatorial interpretations for T of 2n and, of course, T of 0n and T of 1n. And for general m and n, there's a kind of not so nice recursively defined combinatorial interpretation because these numbers T of mn satisfy a recurrence with positive integers, integer coefficients, but there's not, so you can sort of make up a combinatorial interpretation, but it doesn't seem very natural. So looking at something a little different, returning to this generating function 1 over 1 minus x minus y minus z plus 4xyz, we can write it as 1 over 1 minus e1 plus 4e3, where en is the nth elementary symmetric function, and this is in the three variables x, y, and z. So e3 is just the product, the sum of the products of all choices of three variables out of these three. So e3 is just x, y, z. E1 is x plus y plus z. We might wonder what happens to this symmetric function if we look at more variables. So what about four variables? So we take this expression in four variables. Well, we get some negative coefficients. But Kornwinder and later Gillis, Resnick, and Zeilberger showed that if we put in a kind of a correction term, minus 16e4, then we get something with non-negative coefficients. So what about more than 4 variables? Well, you might think maybe we can put in some correction terms like some coefficient of E5 and some coefficient of E6 that will give us non-negative coefficients in more variables. Well, it turns out, at least my observation is that it seems that if you take 1 over 1 minus E1 plus 4E3 minus 16E4, you don't need to add anything else. You get non-negative coefficients in infinitely many variables. Now, I have to say I'm actually a little skeptical about this conjecture. I wouldn't be at all surprised if it turns out to be false, but I did check that it's true up to degree 22, which seems, you would think that if it's false, you would find a counterexample up to degree 22. But maybe not. Maybe there are counterexamples of higher degree. I don't know. So one thing that we can ask a very specific question about combinatorial interpretations of these rational power series. So we'll define the semi-ring of n rational power series in a set of variables to be the smallest set of power series that contain one and all of the variables. It's closed under multiplication and addition, and it also has the property that if f is n rational and f has no constant term, then 1 over 1 minus f is in, that a there should be in, that should be in R. So it's pretty reasonable to say that if you have an n-rational power series, then it has, in some sense, a combinatorial interpretation. It counts certain things that you can construct by operations that correspond to these operations on the power series. One thing about n-rational power series is that traditionally they're only studied in more than one variable for series in non-commuting variables. And in fact, it's easy to see that if you have an n-rational power series in several variables, that according to my definition with commuting variables, then it has a non-commuting version. But on the other hand, if you want to prove that a power series in several variables is not n-rational, then you don't want to start with something non-commutative. So a specific question is, can we prove that this particular rational power series is not n-rational? And one thing to know about n-rational series is that in one variable, there's a very good criterion. If we know that we have a rational power series with non-negative coefficients, there's a very simple necessary and sufficient condition for it to be n-rational. But as far as I know, there's nothing like that for n-rational series in more than one variable. And I should also mention that there's a very nice article by Mireille Bousquet-Melou about n-rational power series that you might look at if you're interested in this topic. Okay, moving on to something somewhat different. These are now algebraic generating functions. They're generalizations of Catalan numbers. So we all know the Catalan numbers, one of our most well-known and popular sequences in enumerative combinatorics. There are a number of generalizations of the Catalan numbers. I'm going to talk about one that is not so well known, although it is somewhat known. So we'll take that 2 in the definition of the generating function for Catalan numbers. It appears twice as 2 squared and 2 in the denominator, and replace that with an integer m. Oh, it also appears in the square root. So we replace the 2 with m in 3 places, and we'll look at these generalized Catalan numbers. So if you just expand by the binomial theorem, you get an explicit formula for the coefficients that shows that they're positive. It doesn't show that they're integers, but it shows that they're positive. And these numbers, surprisingly, were considered very briefly by Euler in a 1751 letter to Goldbach. but he didn't really say much about them. So for m equals 2, they're the Catalan numbers, and we want to show that they're integers. Well, you can probably do this by looking at the power of a prime dividing the numerator and denominator, but an easier way is to look at x times c of mx and then look at its compositional inverse, which is easy to compute because if you set this thing equal to y, it's easy to solve for x in terms of y. And you find that the compositional inverse is given by this expression. And if you expand a few terms, you see that it starts off x and then minus m choose 2x squared. And it's pretty clear that the coefficients later on are all going to be integers because you've got a large power of m here, and you're only dividing by m squared. So the coefficients are integers, and it starts off with an x, and so the compositional inverse will have integer coefficients. So this doesn't show that they're positive, this compositional inverse formula, but it shows that they're integers. So again, we have a situation where we have one formula that shows that certain things are integers, and we have another formula that shows that they're positive. So for example, if we take m equals 3, even in the case m equals 3, there's no known combinatorial interpretation. If you set u equals c3 of x, then u satisfies this fairly simple functional equation. It looks like a kind of variation of the Catalan number generating functional equation, but it has this minus sign, and that means that, well, you can interpret this as counting certain trees or lattice paths with plus and minus signs, but there doesn't seem to be any simple way of canceling the negative things with the positive ones. Okay. So more generally, we can get some related power series with positive integer coefficients, or with integer coefficients. If you take any integers, a1 up to am, it's fairly easy to show that this quotient has coefficients that are all integers. And in general, they won't necessarily be positive. So this includes c sub m of x. It includes this other thing, 1 over 1 minus mx cm of x, which also reduces to the Catalan number generating function for m equals 2. And so this is another Catalan number generalization. And also 1 over 1 minus m squared x to the 1 over m, which is a kind of analog of the middle binomial coefficients, which have lots of combinatorial interpretations. But I don't know of any combinatorial interpretations for any of these. Okay. Now, one thing about these generalized Catalan numbers, which sets them apart from the rational generating functions that I looked at earlier, is that if we look at ordinary rather than if we look at exponential rather than ordinary generating functions, then we do get some simple interpretations. So for example, if I renormalize slightly, if you look at 1 minus mx to the 1 over m, if we look at this as an exponential generating function, it counts m-ary increasing trees in which the root has one child. And similarly for all of those other things, as exponential generating functions, we have fairly simple combinatorial interpretations. So it's possible that looking at them might give combinatorial interpretations for the ordinary generating functions, but I don't know of any way of doing that. So here's another topic. This is something that I've been fascinated by. Nobody else seems to be interested in this, I have to say, but I find it fascinating. I've just been coming across these nice formulas for coefficients of power series of the form f times g to the a, where f and g, they're either rational generating functions or they involve just square roots. And those of you who are familiar with Lagrange inversion know that in one variable, or even in several variables, you can find a lot of examples of this type of thing. You have nice explicit formulas for the coefficients of f times g to the a. But the things that I'm going to talk about do not come from Lagrange inversion. And they're closely related also with the integral factorial ratios that I mentioned earlier. So these things, when you specialize them in the right way, you get power series whose coefficients are integral factorial ratios, and they're not obviously integers. In some cases here, unlike the previous examples, we actually do get combinatorial interpretations, but in most cases we don't. So these all involve what are called rising factorials. A sub n, I'm using the hypergeometric series notation where this a in parentheses sub n is the rising factorial, a times a plus 1, up to a plus n minus 1. And if n is a negative number, we define this in the obvious way. It might not look obvious, but you want it always to be true that you have this recurrence. A sub n plus 1 is a sub n times a plus n. So this tells you how to extend this for negative n. Okay, so these these series are special cases of what are called multiple hypergeometric series. So one of the simplest formulas of this type is this one. So it gives you a formula for powers of this particular rational function. And I've written the exponent as a plus a half. I could have written it as a. I could have changed the a to a minus a half, and I just have the 8th power of this thing. But the right side is nicer if we make it a plus a half. So we could say this is just the power of an arbitrary power of a certain polynomial. So if a is a non-negative integer, then we have this nice formula for the coefficients that is an integral factorial ratio. So why is it an integral factorial ratio? That's because this, well, I'll on the next slide that will be clearer. It's because the thing that we're raising to the a plus a half power, well, if we take the square root of that, so that we're raising something to the 2a plus 1 power, that thing inside, we have a nice explicit formula for the coefficients. Or another way to see it, it's actually, we're taking something, if we were raising this to an integer power, it would be obvious that the coefficients are integers. If we raise it to a power which is an integer, a half integer, as in this case, then we know that the only possible prime that could divide the denominators is 2, and it's not hard to show that 2 is not going to divide the denominator. One other thing that's worth mentioning is it's clear from the left side here that the coefficient of x to the m, y to the n is going to be a polynomial in A. So that says that if you look at the quotient of these rising factorials, all of the factors in the denominator are going to cancel with that involve A. They're going to cancel with factors in the numerator. So for example, you've got an a plus 1 here, and then you'll have an a plus 3, and those will cancel with some of the a plus 1s down here. And then over from this term, you'll get 2a plus 2, and you'll get 2a plus 4, and so on. And they'll cancel with some other factors down here. So we're guaranteed that all of the denominator, these linear polynomials in A in the denominator, they're all cancel. Okay, so we get an integer factorial ratio, and we also get integer, sorry. How did that happen? Oh, no. Okay. We also can get integral factorial ratios by taking a to be a negative integer or a half integer. We get formulas, they're not quite so nice, but we get other integer factorial ratio formulas. So because in this case we've got an integer power of, when a is an integer, a non-negative integer, we have an integer power of something that we know explicitly what it is. So we get a combinatorial interpretation of this number. So it's going to count 2a plus 1 tuples of pairs of lattice paths ending at the same point. And it doesn't seem to be particularly interesting as a combinatorial interpretation, or, it doesn't seem to be something that we really want to count, but it does count something reasonable. So here are some other examples. This is one of my favorite formulas, these two. So these are actually also closely related to the super ballot numbers. And one interesting thing that makes it hard to find a combinatorial interpretation is if we take away this factor of 1 over the square root of 1 minus 4x, or take away this factor in front here, then we don't get non-negative coefficients. And we don't get a nice formula for the coefficients. So this thing here is necessary, and that makes it hard to see how you could find a combinatorial interpretation out of this. We can't just take this thing and raise it to a power. So if we take the second formula here, take a equals b plus 1 and make b a non-negative integer, we get this very nice looking integer factorial ratio. And again, as I mentioned, these are essentially the super ballot numbers. So here are some more examples of formulas like this. They don't always, so for particular values of a, they won't always give you positive integers. They'll always give you integers, but it's easy to figure out what the sign is. So if you want to write them in terms of integer factorial ratios, you have to look at a few cases depending on, for example, whether n minus m here and here are positive or negative. But in all cases, you can write them as integer factorial ratios. Okay. Okay, sometimes I'm having trouble going to the next page for some reason. And here are some more complicated ones. But still interesting. So the questions about these formulas are, my first question is maybe kind of silly. Are they good for anything? It's just these formulas, they look so nice to me. They look interesting, but are they useful for anything? Can we do anything with them? I don't know. There should be some use for them, but I just don't know of any. And is there a unified approach to finding them? So I've discovered these by a few of them are known, but most of them aren't. Is there any kind of unified approach to finding these things that sort of puts them in a, is there a theory of these things? And how do they fit into the theory of integral factorial ratios, about which there is some very deep things known, but these formulas don't really, as far as I know, they don't sit very nicely with this interesting theory. Another thing you could ask, are these things n-algebraic? I'm not going to define n-algebraic, but it's a kind of analog for algebraic generating functions, an analog of n-rationality. They're probably not n-algebraic, but I would have no idea how to prove that. Another thing about this is if you look at these as exponential generating functions, then the coefficients are very simple products. And so it's easy to give them a kind of artificial, unnatural combinatorial interpretation. Is that at all useful? Is it all useful to look at the exponential generating functions for these things? Okay, so much about those things. I'm now going to move on to a totally different topic, Hurwitz series, which are exponential generating functions for sequences of integers. So most of you probably know that the set of Hurwitz series is closed under addition, multiplication, and composition when defined, and division. Division when you divide by something with constant term 1. So some useful Hurwitz series that come up a lot in combinatorics are e to the x. The coefficients are just 1. E to the x minus 1, where the coefficients are Bell numbers, secant of x, tan x, and e to the minus x over 1 minus x, where the coefficients are derangement numbers, and so on. So as I just said, if v of x is a Hurwitz series with constant term 1, then you can divide any Hurwitz series by it and get another Hurwitz series. If v of 0 equals 0, or if v of 0 is some integer other than 1, then this quotient will in general not be a Hurwitz series, even if it is a power series. So, for example, the Bernoulli number generating function, the denominator here is e to the x minus 1, which has constant term 0. This is not a Hurwitz series. It's a very important generating function, but it's not a Hurwitz series. And I've come across a number of elementary functions that are Hurwitz series for no obvious reason. I mean, we can prove that they're Hurwitz series, but it's not obvious that they are. One of the best known is the Genoki numbers, which have, you can write their generating function in two different ways. So the coefficients as exponential generating functions of these two things are the same, except for the sign, and also for the coefficient of x is different in these two. And the Genoki numbers do have a combinatorial interpretation. If you look at the x tan x over 2 form, the coefficients are positive, and they count certain permutations and other things. So most of these examples are actually related to the Bernoulli number generating function in some way. The Genoki numbers are related to the Bernoulli numbers. If we let b of x be the Bernoulli number generating function, then this fairly simple thing, n times b of nx minus b of x, that has integer coefficients. So this is a consequence of the von Stautz's theorem for Bernoulli numbers. And there's another generating function that has integer coefficients that it is related to the Bernoulli numbers. If you take this kx over e to the k of x minus 1, that's just the Bernoulli number generating function with kx for x. Then you multiply it by this thing. And Almqvist and Merman proved that this has integer coefficients. And there's a generalization of this that I found. It requires a kind of curious condition. Every prime divisor of j has to divide h or k. If that is true, then this has integer coefficients. So this is a Hurwitz series. And a couple more. If you look at 2 log cos x over cos of x minus 1, this sort of obscure thing, although it's not that complicated, it's possible to prove that this has positive integer coefficients. And if you look at this curious thing, so it's clear that the only possible denominator of the coefficients could be 1/2, but in fact these have integer coefficients. And in fact, as polynomials in u and v, they have integer coefficients. And there is a combinatorial interpretation for this last example, which comes out of a continued fraction. So my question here is, are these things isolated curiosities? They're all kind of in some way vaguely related to the Bernoulli numbers, but the proofs are all kind of different. There's no, I don't know of any uniform proof for showing that these are Hurwitz series. And is there a theory that explains which elementary functions are Hurwitz series? Is there some nice criterion or some kind of general proof method? And of course, we can always ask if there are combinatorial interpretations, because in some cases there are, but in most cases we don't know of any. Okay, moving on to a totally different topic. There are all kinds of identities in combinatorics that you can ask for a combinatorial proof of, and these are just a few that I've come across that I thought were particularly interesting. So this one involves what are called strong digraphs or strongly connected digraphs. So a digraph is just a directed graph. A strong digraph is one in which for any two vertices u and v, there's a directed path from u to v. So it's not really obvious how to count them. These are all labeled digraphs that I'm talking about. It's not obvious how to count strong digraphs on the vertex at 1 up to n. But there is a fairly simple formula that something equivalent to this was found by E.M. Wright. He found a recurrence that he didn't write it in this form, but he wrote down something equivalent to this, so that this generating function can be written as log of 1 over 1 minus some generating function t of x. And the coefficient t of x, this is the generating function for these numbers t sub n that count strong tournaments, but multiplied by 2 to the n choose 2. So a tournament is a graph in which for every pair of distinct vertices, you have exactly one edge between them, going one way or the other way, but not both ways. And strong tournaments are easy to count. I'll give you the formula in a second. But so what this suggests, so formulas like log of 1 over 1 minus something come up all the time in working with exponential generating functions. And what they usually, or one way to interpret them, is that this means that these things are circuits, are cycles of the things that t of x counts. So what this suggests is that you can represent a strong digraph as a cycle of things, each of which is a strong tournament with some additional information in it that corresponds to this factor of 2 to the n choose 2. And one thing that I can say is that if there is such a bijection of such things, it will depend on the total ordering of the labels. That it's impossible to do this. It's impossible to interpret this in what you might call a natural way or a species theoretic way that doesn't involve the total order on the labels. So I'll just mention that the numbers t sub n, they satisfy this formula, which is easy to prove. This basically comes from the fact that every tournament can be broken up as a sequence of strong tournaments. Okay, so that's all that I have to say about that. Here's another totally different problem of looking for a combinatorial interpretation. So this is counting square-free polynomials over a finite field. So there's a very simple generating function proof using the fact that every polynomial can be expressed uniquely, or let's say every monic polynomial can be expressed uniquely as the square of a monic polynomial times a monic square-free polynomial. So that gives you a generating function relation for all polynomials and square polynomials and square-free polynomials. And the all polynomials and square-free polynomials, those are easy to count. So you invert that to get the generating function for square-free polynomials. And you find that the number of square-free monic polynomials of degree n over a finite field with q elements is given by q to the n minus q to the n minus 1. This is for n greater than 1. It makes sense for n equals 1, but it's not true for n equals 1. And so a natural question is there a combinatorial proof of this simple formula? And it does not seem, I wouldn't be surprised if somebody can come up with such a proof, but I haven't been able to do it. Okay. And this is actually my last topic. I think I'm going to, well, yeah, I'll end maybe a few minutes early, but not too many. So this is a very obscure identity, and I can't blame you if nobody out there finds this interesting, that, you know, I wouldn't be too surprised. But I find it interesting. So this is a formal power series identity that De Bruijn proved using asymptotic analysis. So using asymptotic expansions, De Bruijn proved an identity for formal power series. And my question is it possible to find a formal power series proof? So if we have this relation between two formal power series, it seems to me that it should be possible to prove it without using any analysis. But despite spending a fair amount of time on it, I have really gotten nowhere on it. So it's a really weird looking identity, but when you look at the proof using asymptotics, it makes a little bit more sense. So I'll define b of x now. This is different from the b of x before. It's this kind of funny generating function for Bernoulli numbers. B sub k is the kth Bernoulli number. So we take an x to the k minus 1 here rather than x to the k, and we divide by k times k minus 1. Okay, so this weird Bernoulli number generating function. Now we take u of x to be this kind of strange looking generating function. We take 2x minus 2 log 1 plus x, and that starts off with an x plus higher terms. I'm sorry, it starts off with an x squared plus higher terms. So it has a square root, which is a generating function, a power series that starts off with an x. So this is a genuine power series that starts off with x, and it has a compositional inverse, therefore. And I'll let that be v of x. So v of x is the compositional inverse of this funny-looking power series. And I'll call the coefficients v sub n. So v sub n is the coefficient of x to the n in v of x. And now I take this funny generating function, a sort of shifted or transformed generating function for just the odd v n's. So I take this generating function for v sub 2k plus 1. But instead of multiplying it like you'd think, multiply by v sub x to the 2k plus 1 over 2k plus 1 factorial, I multiply it by x to the k over k factorial. So this is a kind of transform generating function. I throw in this factor of 2 to the minus k. And the formula is that this weird thing is equal to e to the b of x. So this is an identity of formal power series only because both series have radius of convergence 0. This is kind of a nice example of a non-trivial identity between formal power series with radius of convergence 0. And the way de Broglie proved it is he looked at the asymptotic expansion for n factorial, in other words, the extension of Stirling's formula. He computed it in two ways. So both of these are asymptotic expansions of this thing related to the factorial. So we all know that by Stirling's formula, n factorial is approximately the square root of 2 pi n times n over e to the n. If you divide by that, then you get something that has an asymptotic expansion in negative powers of n. If we replace n by 1 over x, then we get a power series in x. And the way that he got these two things are, well, one of them is very well known. The e to the b of x comes from taking the logarithm of the factorial. You get a sum of the logs, log 1 plus log 2 plus log 3, and so on. And you get the asymptotic expansion of that by the Euler-Maclaurin expansion. So that shows you where you're going to get Bernoulli numbers. They come in from the Euler-Maclaurin expansion. And the other side, you use one of the standard methods for asymptotic expansions, Laplace's method. You use the integral for the gamma function, or the integral for the factorial, the integral of e to the minus x times x to the n dx. You make a change of variables, and you make a change of variables so that you can express it as a nice integral. And this change of variables brings in that funny function v of x. And this sort of weird transformation from x to the n over n factorial to x to the k over k factorial with v sub 2k plus 1, that comes in very natural from the integral of another integral for the gamma function. So it sort of makes sense as an asymptotic expansion, but to try to imitate something like that using formal power series, I have not been able to figure out any way of doing it. Okay, that's all I have to say, so I will stop here. Thanks for listening, and thanks to the organizers for this Very nice conference.
Thank you very much for a very nice talk.